All right, howdy folks. Welcome back to the Professor Carbon YouTube channel. In this particular video, what we're going to do is go over an NMR problem shown here. And like with most of these videos, what I encourage you to do is actually to pause the video, take a minute, see if you can come up with a reasonable structure here, and then come back and watch the discussion. It'll really help you learn instead of just listening to me narrate through how I would have solved the problem. So please do that right now. All right, welcome back. For any of these problems with an NMR, one thing that I encourage everybody to do is to first explore the degrees of unsaturation so that we can understand how many rings and or double bonds should be in our molecule. And so as a brief reminder, remember any saturated hydrocarbon, regardless of how long the chain is, has 2n plus 2 hydrogens. And I always think about that as being one hydrogen for two hydrogens for the methylenes, and then one hydrogen for each end to kind of cap the chain, if you will. And so we can also ignore the oxygen count for the purposes of calculating degrees of unsaturation. And so if we have C7, 2 times C would be equal 14, and then we would add 2 to it. So we would expect there to be 16 hydrogens in a C7 molecule. Then what we can do is subtract off the 12 that we have, and so there are 4 missing H's. And then usually we divide that by 2 to get the degrees of unsaturation. And the reason for that, remember, is if you take a double bond and you hydrogenate it, you add 1 H to both sides. So every degree of unsaturation is 2 missing hydrogen atoms. So because of that, then we would have 2 degrees of unsaturation in this molecule, and we would have to account for that. Remember, each degree of unsaturation is either going to be a double bond or a ring, and so we'll have to figure out which of those two it is down below. So the next thing I usually tell folks to do is to try to identify all of their key clues, and of course it's easier said than done. And the reason it's easier said than done is, after you look at 1,000 NMRs, you'll have a good opportunity to recognize some patterns, and the unusual things will kind of just pop out at you. Unfortunately, when you're starting out, there isn't a great way to recognize what the unusual peaks are until you kind of build up that familiarity. So that's kind of what we're here to help with. Okay, so real quick, looking at this data, one thing that just kind of leaps out at me is this peak. And if we count, it's 15, so that would be 16, 17, so that looks right about 17, 15-ish to 17, 25-ish, and that is a dead giveaway that we have a carbonyl carbon in this molecule, and that's important because that takes care of one of our degrees of unsaturation. Now if we go look in the C13 NMR, this peak at 170 will tell us that we have to have an acid or an ester, because remember, ketones are at about 200 to 210 ppm, and aldehydes are usually right at about 190 to 200. And so because of that, this 170 peak right here tells us right off the bat that we have to have an acid or an ester to account for this IR shift in the carbonyl range. So it can't be a ketone based on that carbon NMR. So that's pretty good. And while we're keeping track here, why don't I just put some peaks like this on that ester for where our kind of blank spaces are. And the reason I'll point out that it's probably going to be an ester is we don't have anything here. And the other really important thing that we can always do early on is just count how many H's we've got. So we've got 3, 6, 9, 10, 11, 12. And we'll notice that this cuts off at 6, but that's okay because we actually have all 12 of our H's. And so between the NMR, the 1H NMR, and this IR, there appears to be no OH H's in this molecule. Remember, for a carboxylic acid, if we had that OH, this should be down at like 12 ppm, and it might be a little broad, and we'd definitely expect to see something in this region in the IR as well. And so the combination of those missing peaks, and you want to be careful here because we shouldn't really interpret the absence of peaks, but in this case, those signals as a pair are pretty diagnostic, where I think we should at least operate preliminarily on the assumption that we have an ester here. And that's convenient because then we have 2 groups here that we have to assign as being on the left side or the right side of the ester. All right, let's look for some other obvious clues. As long as we're looking at the carbon NMR, we happen to have not one, but two signals in the double bond region. And so remember, from about 110 all the way up to about 160 ppm is where we have our C double bond C. And that's really important because that, if you have one double bond, that would be our second degree of unsaturation. And the other thing that's really important about that then is that helps us explain this peak out here, which is clearly in the double bond region of the 1H NMR. So definitely we've got a double bond, and that double bond's got one hydrogen on it. Now you might ask about this signal. That one's getting pretty close to the double bond region, and so we should probably consider that it might be on some kind of very electron-rich double bond, but being well below 5, it would be a fairly atypical double bond resonance. Still something we might want to consider, and we definitely don't have enough evidence to argue against it. Okay, next big clue, I love singlets. So if I'm going to look in the 1H NMR for a dead giveaway signal that'll help me put a group in place, it's going to be a singlet for 3 H's. And the reason for that is that always has to be some isolating group plus a methyl. And not only that, usually the chemical shifts of that methyl signal will be quite diagnostic, and we'll be able to make a pretty good guess as to what kind of methyl it is based on the chemical shift. All right, and so in this case, that looks like it might be at about 2.2 ppm to me. It's definitely above 2, and it's definitely well below halfway up to 2.5, at least based on the hash marks we're given. And that's a really important range. And so remember, your generic old methyl group sticking off of anywhere that is just hydrocarbons tends to be at about 0.9 ppm. Those that are next to carbonyls, or those that are bound to an arene, appear in this 2.2 region. And so the good news is we don't have a benzene ring in here, so odds are good then that it's going to be next to that carbonyl. Remember, if it's going to be next to an amine, let me go on the other side here. So these might be like 2.5 to 3. And then if it's next to an oxygen, I might expect it to be 3.2. And certainly if it's part of an ester, I would expect it to be closer to 4.0. And the reason for it is that ester is going to move it downfield quite substantially. All right, so based on this peak alone, what I would propose that we have is a methyl ester hanging off. So I'm just going to put that down here. I'm going to label that peak as being this peak here. So I think I'm comfortable with that. And now I've got a couple of other clues here. So the good news is the 60, that's in our oxygen land. So that's going to be the one directly bound to the ester. And then I've got 3 other peaks here. One of these other peaks has got to be the carbon that is associated with the hydrogen resonance A. And so really there's only 2 other ones. And the good news there is I've got a couple of other methyls. So let me go back to this triplet-y looking thing that we kind of brushed off so far that would be on the double bond. If that's really a double bond with one signal, then I have to somehow fill the X, Y, and Z spots on this double bond. And for me to get a resonance down this far, that is, kind of on the upward edge of where we might expect an ester to be. So if we just had a CH2 here, we might expect this to be at like 4.2 ppm if it were, let's say, ethyl acetate, so the exact molecule I have drawn here. That would be right about here. But this one's dragged even further down. Not only that, these methyls over here, these are nowhere near that 0.1 gauge that I gave you, or sorry, 0.9 range that I gave you before. They're all the way, above 1.5. They're at, 1.6, 1.7, 1.8, somewhere in that range. And what that tells me is that these are going to be methyls next to a double bond. They are allylic methyls. And so that double bond has electrons spinning around it, and it's actually going to shift all of those peaks just a little bit further down downfield. And so being next to an allylic, or being an allylic center next to a double bond really does make a small difference to the NMR. And because we have the double bond that we're worried about, being able to assign or interpret those as being allylic actually can be quite convenient. Now, if I have two different allylic methyl groups, then I could imagine assigning this a couple of different ways. So I could have H, CH3, CH3R, and let me just make that our ZAG O, because that's really what we've got left. So this would be okay, except we have this nice coupling here. And my 0th rule of NMR is if you're coupled to me, I'm coupled to you, and we're coupled to each other the same. And the distance here looks like it's about 1 pen line, and the distance here looks like it's about 1 pen line. And so those look like about the same couplings. And I'm just going to undo that so we can have our peaks back. All right, and so what that means is that these two are talking to each other, and they're coupled, and so they've got to be next to each other on the system. So then the only way to do that is to have H and then have our H's over here. And now we would expect these to communicate with each other. And so that means that what's left has to be our methyl groups here. And so that completes the molecule then. And again, going back over it, really the key pieces of information to pick up here, one very important clue is this carbon resonance at 170. That tells you you've got an ester if you combine it with this IR shift at 115. So if you missed that, it would be more difficult for you to solve this problem. Still wouldn't be impossible. The next thing is we've got 3 methyl peaks here. And it's very cool that we can take advantage of this chemical shift information and recognize that they're not your standard old methyl carbanes. Not only that, they're definitely not where we'd expect esters to be or ethers to be. And so because they're upfield of those, we know from that chemical shift information that they're not directly bound to an oxygen. And that really helps us propose that they're the acetate as well as the allylic methyl groups. Now, one fun thing I didn't mention for those of you that are experts is you'll notice that this methyl singlet is quite a bit taller than these. And it turns out that these methyl groups are split with a very, very, very small coupling constant. And if you look, this triplet is also a little fuzzy on top. And because it's a little fuzzy on top, it has that same coupling. And it's an allylic coupling. It's kind of a long-range coupling. Sometimes it's called a W coupling. And so if I put that H on a double bond, and then I have the methyl H's here, and I sketch this out, you can see that you can get a W. So sometimes it's called a W coupling. Often it's very, very small. Often we actually miss it in the NMR unless you deliberately go look for it. And what it does is it just is enough of a splitting to make those peaks just a little bit wider. And of course our integrations are based on area, and area, simplified is base times height. And so if you make the base a little bit wider, the height has to drop to compensate to get the same integration. And so these slightly wider methyl groups are kind of illustrative of an allylic coupling. So that's kind of fun. And you of course can see that over here in the triplet signal as well. All right, so if you're enjoying these videos, please do subscribe to the Professor Carbon YouTube channel. We still haven't broken 100 subscribers, but I'm very excited we'll do so soon. And please go ahead and give us a like on your favorite social media as well. Thank you.